evening, good evening, good evening. Put my meteorite gavel. It's, oh, I wish it was. I do have some uranium glass at home. I've got some TESS to wear from the 40s. That's nicely radioactive. An old americium 241 source out of the bus. I busted out the smoke detector once. It's good to have a little radioactive.
Physics today.
Nice. One of my favorite, one of the books I'm reading again is Atomic Accidents. That's a fun read.
You ever have uranium cube?
I don't. I wish I did.
Call it.
We'll talk afterwards. Well, good evening, everybody. Of course, my name is Rich Nugent. I'm your vice president. Tom McDonough is out in California on business, so I have the pleasure of running the show tonight. So it's the 920th meeting of the Amateur Telescope Makers of Boston. Welcome, everybody. As you all know, ATMoB has been around for quite some time, founded in around 1934, and combined with the Magellanic Astronomical Club in 1973, making it one of the very best astronomy clubs in the whole world. So welcome tonight. We have a nice meeting on store for you guys tonight. We do have some business to take care of later on. We have to elect the nominating committee for next month's elections, and I think we're a month behind on that, but it happens. So anyway, we'll take care of that later on. But we might as well get the show on the road so we're not here all night. All right, observing committee. Observing committee. Well, Glenn isn't here tonight, and Bruce asked me if I would do it for him, so I'm going to do the observing committee. So there's Glenn's, well, it's Ken Fulton's quote. Always been a special pleasure knowing that when you look upon that distant light, it has traveled all those light years. Such an incredible journey just for you. And I know Glenn starts off his monthly report with up-and-coming events. So, on Friday, May 10th, that's tomorrow. Tomorrow night, the moon will be crossing through the Beehive cluster. That's always pretty to look at. On May 28th, if you're a fan of Asteroids, Ceres reaches opposition. And there must be finder charts in the May 2019 issue of Sky and Telescope. Pages 48 and 49. Jupiter is in opposition on the 10th. And I plan to continue. Do we have any clear weather on April? Jupiter is actually starting to show up around midnight now in the southeast. And so I'm going to continue to send out information regarding the passage of the Great Red Spot. It's really quite vivid, just like it was last summer. And if you've never taken the time to look for it, yeah, it's really pretty easy to see. Last summer I could see it even in my 60 millimeter refractor. So it's a very pretty orange color, and it's I'll continue to pass that stuff out into the fall, just so you'll know when it's going to happen. And speaking of Jupiter, on Tuesday and Wednesday night, June 11th and 12th, there are the times, a double shadow transit of Jupiter's moons Io and Ganymede. So that's always fun to watch. And if you have a relatively large telescope, especially as Jupiter nears opposition, look for the moons as disks. They subtend a few arc seconds. They're small, but you can actually see them as disks if the weather's cooperating and the seeing is nice. And so you should try that. You should definitely try that. It's kind of fun. Yes, sir.
Regarding the occultation, I'm sending something out as we speak to the announcers. So a little bit of detail with some links to more detail. One to look at.
Excellent. Yeah. If you've never watched an occultation, some people haven't, it's worth checking it out. And when the moon crosses the Beehive, of course, it's a nice rich star field with lots of occultations. You can prove to yourself that the moon has virtually no atmosphere because the stars are at full power, full brightness. And then when the knife edge of the moon covers that infinitely small point of light, it literally winks out. And if there were an atmosphere on the moon, you would expect that the light would get dimmer and dimmer and dimmer before it actually went out. But you can prove to yourself, and the brighter the occultation, the more dramatic it is. But I like to look at the little faintness too. They're kind of fun to watch. So we'll have to thank Glenn for all that. The Observer's Challenge, this is Roger Ivister's Observer's Challenge. If you tried the ones for April 2964 and 2968, you know they're faint. When you look, if you read his report, when you look at my sketch, I even suggested in my write-up that my sketch is best seen in a dark room. because and Roger said, "Oh, what a beautiful sketch." I said, "Roger, they're just two little smudges on a piece of paper," because that's really all they were. They're tough galaxies to reasonably tough to find and even tougher to see. But the ones for May, NGC 4036 and its little companion 4041 are actually relatively easy to find. This is the bowl of the Big Dipper, and I'm going to show you a screenshot from Sky Safari Pro. But those are two easy galaxies to see, and they're actually fairly bright. Glenn said, if we, do I control the lights, or I do control the lights, don't I? Do I dare? No. Well, these are actually fairly bright smudges. But what I was hoping to show is that the ease of finding this galaxy. I'm going to go back a slide.
Simulated light pollution.
Very much so. So here's the bowl of the Dipper. And just to the north of the bowl of the Dipper are 3 stars that will probably most likely show up in your finder scope. This star here forms a nice triangle, a nice skinny little, almost isosceles triangle with those 3 stars. These are easy to find. That's easy to see. And 4036 is right in the middle of those guys. A pretty bright galaxy, pretty easy to find. So if you've never done Roger's challenge, the Observer's Challenge, this might be a good month to start. They're very high in the sky in the early evening, and so give them a shot. Glenn sent this sketch. Glenn told me this was known as 4-inch telescope, so you can see them in a 4-inch scope. And our member, whose name is now Doug Paul, took this image. I don't know what instrument he used, but I don't think it's ginormous.
He used basically a camera, 400 millimeter lens with a
there he is right there.
142 millimeter aperture.
Okay, so small aperture. These are pretty easy galaxies to check out. Thanks. Questions, comments? Anything? So, as I mentioned, tonight's speaker is Dr. George Ricker, and the title of his talk is the Transiting Exoplanet Survey Satellite TESS Update. Dr. Ricker is the principal investigator for NASA's Transiting Exoplanet Sky Survey TESS Explorer mission, which was successfully launched in April of 2018. He is currently the director of the Detector Laboratory and senior research scientist at the MIT Kavli Institute for Astrophysics and Space Research. Dr. Ricker received his undergraduate degree from MIT in physics, and an MS in astronomy from Yale University, and a Ph.D. in physics from MIT. Let's give a nice warm ATMoB welcome to Dr. Ricker.
Okay, well, TESS is the acronym, and it's kind of evident what it means. It's a project that was approved by NASA for flight in 2013. And all the people in these organizations down here have worked very hard over the last 5 years to make it a success. In fact, there's been more than a million person hours that have gone into this. Am I okay without a mic?
I think for the recording, is he recording?
Is he recording?
All right.
Yeah, I think you need the mic for the recording.
Sure, I'll be happy to do that. Okay, does that help?
Yep. Yeah.
Okay, great. All right, so this is what TESS looks like. I'll show you some more pictures that have a little bit more detail later on, but it's a relatively small satellite. It's about as tall as I am, and it weighs a lot more. It's about 300 kilograms. And it has 4 cameras, and I'll cover some of the operational details as they go on. The basic idea behind TESS was to look at the sky in as wide a field as we possibly could achieve to look for transiting exoplanets, with a special focus being on planets that are Earth-sized or maybe a few times the size of the Earth, with a special focus on rocky planets and potential water worlds, with the idea that we're going to try to find the systems that potentially are habitable. TESS itself can't establish whether they're habitable or not, but at least it prepares the way. And the process, we're able to make a large area survey of bright stars. Unlike many astronomical satellites, we're really looking at very bright stars. This is unusual because normally people are looking at stars that are fainter than 20th magnitude. So the focus on TESS is actually to look at stars that In fact, many of which you can actually see, going all the way up to second magnitude, and in fact even first magnitude. And we're focusing on M dwarfs because with the way that the satellite actually operates, it extends out into the near infrared, and M dwarf stars tend to be cooler than the sun, so that's another reason for the focus. So we're going to look at 200,000 target stars altogether with a 2-minute cadence. That is, we're looking at the change in their light every 2 minutes. But in addition, we're doing full frame images at 30-minute cadence. And then this will allow us to cover 20 million stars altogether that are really studied with exquisite detail. So just to refresh everyone as to what a transit actually means, this is a circumstance in which a planet is actually lined up so that it rotates around its host star in the plane that happens to line up with our line of sight. Someone asked a question at dinner tonight, well, how common is this? It turns out that for a star the size of the sun and a planet like the Earth, these transits typically last 10 or 11 hours, and the period at which they recur is whatever the orbital period of that planet would be. So for example, in the case of a sun-like star with an Earth at an orbital distance of a year, you're going to have this change in light that would be about a half a day once a year. So you're looking at a probability of actually seeing something like this of 1 chance at about 700. But more than that, if you're saying we're going to be able to see these things when they're actually edge-on when we're looking at them, the probability of that is about 1%. So that's one of the reasons why we have to look at a lot of stars in order to make sure that we actually see an event like this take place. And then if you do so, you're looking for really tiny transit depths, because this dip in light that you see is, in the case of the Earth around the sun, it's about 80 parts per million. So your photography has to be really good in order for you to see Earth-sized planets. And in fact, when you do so, this is a static representation of that animation. When the planet actually passes in front of its host star, you not only are able to measure the size of that planet based on the percentage area that it covers of the host star, but this little blue ring indicates that if light passes through the atmosphere, you can actually analyze the composition of the atmosphere by looking for absorption or emission features associated with it. And then those with sharp eyes who were looking at that animation before, you can see the fact that the planet will actually show phases, and those, just like the moon does, and those phases can be used to study atmospheric circulation. So there's an enormous amount of information that finding these objects, which only requires photometry. You're not imaging the planet, you're only observing the way in which it blocks or impacts the light that's transmitted from its host star. And then if you're really working at it very hard, you've got something that works in a very broadband way, then you can see the thermal radiation disappear and reappear. I'll grab this. So here. All right, let me get this back. Okay, so that's the basic information. Now, the way that TESS itself sort of fits into the overall picture, this is a chart that NASA prepared of all the exoplanet missions that have gone before. Kepler is the one that people have heard most of. Spitzer, which there's been work by a number of people here. Dick was telling me about his experiences. Dick Taylor at dinner. Hubble, of course, makes these observations. And TESS is midway between Kepler and Webb, and its role with Webb is an interesting one, because TESS is launched in advance of Webb by about 3 years. But more than that, this is a picture of what Kepler looks like when it's deployed, and this is what TESS looks like. Not only is it smaller, but it basically is, you can think of it as a finder scope for Webb. And that's one of the key things. As it turns out, there is no such capability on Webb itself. So TESS has been something we've been thinking about since around 2006, and there were a lot of conceptual studies that we had to do. Initially, it was bigger. It actually had 9 cameras associated with it, and then we studied it further and figured out what it would cost, and then it shrank to 6 cameras, and then we finally, in the version that we are actually flying, it only has 4 cameras. So this was mainly financial realism in terms of actually figuring out how much things would cost, but it also reflected the fact that the cameras themselves had more capability than we thought, and we could get by with a smaller number. So the other thing is, if you're familiar with the discoveries that Kepler has made, they found that mission has altogether found about 3,000 planets, but it did so by looking at a very narrow portion of the sky, 1/400th of the sky. And whereas TESS's idea is to look all sky, and it does basically what astronomers refer to as a shallow wide versus a deep narrow search. So these are complementary ways of finding interesting objects in the sky. So the field of view of TESS is really enormous. It's 2,300 square degrees. So that means that every time we take a picture of the sky, we're looking at 6% of 4 pi, the entire sky. So I'll give you some examples that show that in this slide. This is an image that shows what we get from one of the 4 cameras, and it's 24 degrees on a side. And by comparison, you can fit 10,000 moons within this field of view. It's 2,300 square degrees. And this is the size the Kepler field of view had. So Kepler is roughly 1/20th of the size of the field of view that TESS has. And then these are 2 of the largest ground-based fields of view that astronomers have put together, or in the process of putting together. The large synoptic survey telescope that will come into operation in 2022 has a roughly a 10 square degree field of view. And this is the old Palomar-Schmidt telescope that's been repurposed as something called the Zwicky Transient Finder, and it hits 47 degrees. And so what TESS does is that with these full frame images, you get every single pixel with every single star, every single galaxy in this at a rate such that you get 1,300 successive images with all the cameras for every sky segment, and this happens every month. So it's a long sequence, and you'll see as I describe some of the material later on why this is such an important thing. So this is another way of looking at the solar neighborhood for TESS. This is the sun in the middle, and we're sort of taking the God's eye view of our part of the galaxy. This is RA around here, and when you see the little dots as I run the animation, you can see where they have been discovered by. And this animation shows Kepler and what we have predicted for TESS. And if I do this right, okay, now I'll sort of pause at this point. So these are in parsecs. So according to the simulations that we did, we expected to see a habitable zone planet about 5 parsecs away. That's the temperature in Kelvin. So then 0.9 Earth radius, that's pretty good. And if you let this run a little further, this is what we expect as we go further and further out. And you notice that in this, all the way out to 30 parsecs, 100 light years, you're seeing these occasional blue dots that were established primarily from ground-based searches. There aren't very many of them, but all the rest of the objects are those that TESS will expect to find. And if I let this run all the way out, then you see that spray of black and gray stars that are going off to the side. That's that cone going out that Kepler discovered. Again, so it makes the point, if you want to look at things that are nearby, this is a good way to do it. Now, if you plot distance along this axis and the planet radius, because we're really interested in finding small planets and not just giant planets are relatively easy to find even from the ground by the transit method. You want to find things that are in this general region. Kepler found a lot of things out here, but the problem with the ones that they found is that they're too faint to follow up, because if they're fainter than about 12th magnitude, 11th magnitude, you just don't have enough photons to do the follow-up in a way that you end up being able to analyze the composition of the planet's atmosphere, or alternatively, you can't even determine its mass, because the transit method only tells you how big the planet is. It does not tell you what its mass is. So you have to use that by a radial velocity method, in which you measure how the planet is actually tugging on its host star and moving it back and forth, and therefore the spectral lines move around. So then if you put in the TESS planets, this is where they lie, and these are all within a couple of hundred light parsecs, and so this is really the hunting ground for a mission like TESS and for future explorations. So this is a close-up of what TESS actually looked like when it was being prepared at the spacecraft Victor in Virginia before we shipped to Cape Canaveral for the launch last year. So these are those 4 cameras that are set up here, and there's solar panels that are being deployed, and this is the dish that brings the data back to the ground. So this is when we arrived at Cape Canaveral. This is the fairing of the Falcon 9 rocket that we were going to fit into, and you can see there's a person sitting over here. So it's quite a big thing. And then if you say, well, okay, this is the size. It's pretty impressive. You can put a school bus in there, and this is what a satellite looks like. So it's a little bit of an overkill, but this is what happens when the government puts out a contract to an innovative company, and then they actually say, well, this was the low cost bidder, and that's what we ended up with, which we were not unhappy about, as opposed to a rocket that we'd have to squeeze tightly to get into. So this is what it actually did look like. This is the satellite, and then this is an adapter cone that goes down to the second stage. So the whole thing is really enormous. That's what it actually looked like as we were getting ready to launch. Was there anybody in the room who was actually there for the launch? You were
Sort of.
Okay. All right. Okay. All right. Then I'll
Delayed it by a day.
Yeah. We were originally going to launch on the 16th of April, but we ended up launching on the 18th. And so, all right, in that case, I'll show you this. Hopefully, the sound will be loud enough if I can put it together. It may not be, depending on, so we'll have to be a little quiet because it looks like it's only going to come from the computer.
Stage 1 is at starting pressures.
T-minus 15 seconds.
Falcon 9 is configured for flight.
10, 9,
This launch was at dusk, and it's really a beautiful thing to see.
5, 4, 3, 2, 1.
Launch flight operations. England's pitching penetrating. Stage 1 propulsion's nominal.
As you just saw, Falcon 9 has successfully cleared the path and is now on its ascent with the TESS spacecraft in its fairing.
So then what happened 45 minutes later, the launch was very successful. And then we had first stage burnout, and then the second stage burned for about 5 or 6 minutes. and then there was a coast phase, and then it burned again, and then this is what we saw from a camera looking up at our satellite from inside the fairing as it lifted off. And this to me was the most exciting part, because then at that point we knew we were going to have a chance to actually operate in space as it was designed to. So the thing that we also had to do is we had to insert into an orbit, and the orbit that we chose after we did the launch was an unusual orbit. It actually is what's called a lunar resonant orbit. This type of orbit has never been used before, but basically after we left the Earth, we went into this highly elliptical phasing orbit, and we went to an apogee of about 270,000 kilometers initially. The moon is out around 400,000, and then we sort of went around this racetrack, and we give ourselves a little bit of a boost at perigee every time we passed through there. And then on the third time, we had timed the launch in such a way that after this last burn, the moon was coming by where we were going to be. And then when this worked out, we did a lunar flyby, and that flipped the orbit up by about 37 degrees. And the reason that was important was if we had stayed in the ecliptic, then every month we'd have the moon and the Earth coming into our field of view, and that would be a real problem. So by going into this highly elliptical orbit, we accomplished two things. One is we come back to the Earth every lunar month, and that gets us close enough that we can dump enormous amounts of data, but yet we don't have the disadvantage of being so close to the Earth that the Earth is always getting in our field of view, so there's scattered light from it and the other problems that come from that. So this is the other nice thing about this orbit is that if you see the way that TESS goes around, that's TESS going around the Earth, and the moon is going around. When we reach a point like this, when it's about a 90-degree angle between TESS, the Earth, and the moon itself is actually tugging on the orbit, and it's pulling the orbit down. And then if I let it run, and then it goes around a week later, then the orbit is being perturbed in the other direction. And as a result of this, what happens is the orbit will wiggle back and forth a little bit, but it's stable. And we planned this in such a way that if we did it right, the orbit is stable for decades, and we don't have to use any fuel. We're basically stealing energy from the moon in order to make this work. And being able to come in close to the Earth means that we're not in a situation if you go out on a planetary probe and you have to use, you can't bring your data back at a very high data rate. So this is one of the neat things about this. So then there's some complications that come into place. This is year along here, and then this is distance from the Earth for the perigee at least. And these oscillations are the fact that it's what I was talking about before, that this 9-year period, that's basically the rocking back and forth that occurs, and then these higher frequency motions that you're seeing are due to the sun and the Earth and the moon acting together part of the time and opposing each other the part of the time. But the bottom line is that the orbit, this particular period of time is 25 years. This oscillation just quietly goes along, and we've got a stable orbit behavior for more than 25 years. And in fact, we put a lot of extra fuel in the hydrazine system that flies along the satellite with the thought that we might have to use it, but the rate at which we have to use it is we've really got enough fuel for 300 years, so that's not a problem. Yeah, exactly. So anyway, these are the kind of things that you get out of this orbit. You can do really extended observation. There's no day or night oscillations or anything like that. You're able to observe continuously. The stability thermally of the satellite when you're in this orbit is incredibly good. It's a millikelvin per hour, so that means that there's no drift into CCDs or anything of that sort. that's temporally and thermally related. We're well away from the Earth and the Moon, so the stray light's a million times lower. We're outside the radiation belts, and we just don't have the kind of problems that you have in a low Earth orbit or certainly what you would have on the ground. And this is the wonderful thing, is we can bring down data at incredibly high rates, and that means we can bring back those full frame images, which has not ever been possible with any of their missions. Go ahead.
You're outside the Van Allen belts?
Yes, yeah, we stay outside the Van Allen belts. And we stay above the geosynchronous belt, because that's an international regulation in case you might bump into somebody or whatever. Then the way we actually bring the data down is we just make one contact every 2 weeks, and then we enter the
You going to talk about the cameras at all?
I'm going to talk a little bit about the cameras. So anyway, this is just how things turned out. The photometric noise floor is really low. It's low enough to the point that you could actually detect planets significantly smaller than Mars, or even half the size of Mars if need be, especially if they're around smaller, cooler stars. And the plane jitter, this is the other thing that's really happening, is the CCDs have 15 micron pixels. They're very similar to many of the ones that are the commercial ones, the Kodak systems that people have been used. The stability is 1,000th of a pixel in terms of the way the satellite and the cameras. In terms of guiding stability, this is something that no one else has ever done before. This is even more stable than Kepler was. So ideally, you get the performance that you get out of the system is what the CCDs are theoretically possible for. So anyway, we spent 3 months trying to commission the system and succeeding, working out, trying to understand how to tune the cameras up and get optimum performance. And then we began our science survey last July. And then we actually, this animation here will actually show the way that we actually map out the sky. Basically, we put one edge of the field of view. The cameras have the fields of view splayed the way my fingers are right here, with one pointing up at the ecliptic pole and then one pointing up near the ecliptic. And then basically with that stripe, which is 96 degrees long, you're able to look all the way from the ecliptic pole to the ecliptic itself. And then as the satellite and as the year progresses, we're constantly looking in the anti-sun direction. So the fields that we actually have are all arranged in such a way that for ground-based astronomers, these fields, as they are taken, are actually the fields where the stars and galaxies are crossing the meridian at midnight. So we did this to make it very convenient for ground-based follow-up. And so that's what this shows. So that means we've got something that we refer to as continuous viewing zone, which also is the one that's associated with the Webb telescope when it launches. So this is just what I said, with the 4 cameras, each of which has 4 CCDs, and they're stacked in this way. So if we'd basically be going to, if you took the size of this structure in that image that I showed you initially, it would be going up 4 stories. And then this is another view of that. And then when we're done, you end up mapping the sky out in these orange slices, basically, and they're gaps. And we're going to fix those gaps in an extended mission. So around in this area here, we're going to do one. We started out with a southern hemisphere, and then this July we're going to switch over to the northern hemisphere, and that means we've got a year of coverage in this zone up here of about 600 square degrees. So this is the image this is the first flight image that we got when we started observing, and this is in the southern hemisphere. So this is the Large Magellanic Cloud, and this panel right here is blown up over here, and then this one over here is over at this side. So there's the small Magellanic Cloud, and there's a lot of really interesting objects that it turned out that are in this field around the LMC. Now, when we switch over to the northern hemisphere, we'll be looking at, we'll have another continuous viewing zone that will have an area near Ursa Major, actually. It's actually in Draco, that will be close to where that will correspond to this location when we're there. So the way we map across the sky, the very first sector that we took last year was in this stripe. This is in ecliptic coordinates, and then as we step around, these are the 13 that we're going to have for the initial survey. And if you turn this into astronomers' coordinates, celestial coordinates, this is the things that are tipped up because of the 23.5-degree tip of the Earth. And then this area up here for sectors 4 through 8 was surveyed in the northern hemisphere. Sector 8 was back in January, so the period from October through January, we were actually looking at fields that northern hemisphere observers could see. In fact, there were quite a few people who actually participated in that. Now, this is another way of viewing those images. And then this is the Large Magellanic Cloud. So this montage actually shows if you were in the southern hemisphere looking toward the Large Magellanic Cloud, this is the field of view that you would see almost horizon to horizon from that configuration. Now this only has 8 of the sectors at the time this image was made, which was about 2 months ago. We're now doing sector 10. Then you can see the gaps, and those are the things that we'll be fixing later on. There's a portion of the galactic plane going through here. One of the things that happens, because the TESS imagers, the CCDs, are quite deep, we actually measure all the way out to 1 micron. And so we can see through a lot of gas and dust extension that otherwise is a problem in the visible band. Now this is something that's interesting that we saw. This is a 10 square degree field out of the 2300, so it's 0.5% of the field of view that TESS is looking at any given time. And these are 50, this video when I show it will be 50 30-minute exposures stacked in sequence. And if I do this, this is what it looks like. So what's happening, you see there's several things that you can see. You can see the asteroids coming through, and there's a lot of them. You see stars that are blinking. These are variable stars, and so this is an animation of that. And then the other thing that's really quite neat is you'll see these little things that look like shadows that move around very slowly as the image goes across, and then there's sort of a jump that occurs right there. That's caused by velocity aberration, and that is the satellite itself. It's a relativistic effect. The satellite itself is actually moving at a fairly high rate, and so it causes a slight shift in position of the stars in the sky, and that's something that we can correct. So altogether, we've seen thousands of asteroids with the system. They're just there. It depends on, if you're interested in asteroids, this is a great thing, but many things we're trying to do, we just wish they weren't there. Anyway, so that's how that works.
Mario has a question.
Yeah.
So I imagine you're going to pick out, I mean, the actual planets are going to be minuscule to be able to show them there with the variable stars. You're doing this by automation, by stacking and looking and subtraction and looking for residual.
Yeah, and I'll show you what some of those light curves look like. Yes.
What is the resolution per pixel, arc section per pixel?
It's relatively coarse. They're about 20 arc seconds on a side. They're 64 megapixels, and the reason is we're trying to cover a large part of the sky, and we're trying to use CCDs that have very high performance. These CCDs, they're pretty big. Each one is about so big. Each camera's field of view, which is 4 CCDs, is about this big. So it's a very large focal plane that we're actually having to deal with.
20 arc second per pixel.
It's 20 arc seconds per pixel. And the thing that because the one thing that we've learned, we predicted this and it turned out that it works, is because the system is so stable, we can actually super resolve the pixels. So there can be 3 or 4 stars in a given pixel, and we can actually look at the weighted averages of those. And we also have a great catalog now, the Gaia catalog that just came out in time for us to use it. So now we know where the stars are located, so we can actually deconvolve the information photometrically from it. That's proved to be very important. So I'm going to show you some of the results from the exoplanet discoveries that have just been made over the last few months. Well, this is being done, at least in terms of identifying the objects, by we call these things objects of interest. It's sort of like the detective story, because we don't know for sure that they're planets until we undergo a fair amount of screening. And there's a team of grad students and postdocs and staff people, everyone else sort of pitches in to do this. We're doing a lot of this work initially by hand. We've developed some machine learning tools that have been checked out over the last few months, and we're able to do some of this in an automated way. But there's a lot of work that's being done by this group. So most of what I'm showing you, these people are astronomers, but they're also doing the grunt work that has to be done in order to make this a success. So it's a great team, and we've been really very pleased at the way everyone's pitched in to do these jobs. So this is the other thing that we do is once we've identified the planet candidates, there are things that can falsify a planet signature. Like if you've got an eclipsing binary, that can, if it's a grazing eclipse, that can look like a planet even though it's just 2 stars. And there are quite a few other artifacts of various types that we've been able to identify. So you want to, if you possibly can, there are a number of screening methods that we can use. If the planets are very big, you can actually do, you can ask ground-based observers to look for a transit, because once TESS is determined that there's a suspicion that you've got a transit, we can predict exactly when it should be, so people can use their telescope time very efficiently for the follow-up work. So what actually happens is we've got 100 institutions on 6 continents, and so far we've had 564 candidates, and all, as the numbers screen by, you can see there's radial velocity, all these other things that are going on to actually try to understand what we're actually seeing. Now, this map is a little misleading, because you notice that most of these facilities are in the northern hemisphere. So the bulk of this work has actually been done by these groups in Australia, New Zealand, and there's one facility in South Africa, and there's a bunch of telescopes, as you probably know, in Chile that are coming. Now, when we switch over to the northern hemisphere, which happens in July, we're going to have a lot more follow-up work that can actually be done, including work that amateurs are actually doing as well. So far, we've found 38 masses. We told NASA when we started this project that we would do 50 masses in 3 years, so we're way ahead of schedule. We're a year ahead of schedule, basically, in terms of our progress on this problem. This is one of the nice images that we had right at the beginning. There's the Large Magellanic Cloud, again, staring at the south ecliptic pole. And this little object up here is a 5th magnitude star. So Pi Mensae, it's a naked eye object. And what this particular object was known to have an interesting giant planet. This is a planet that's it has 10 times the mass of Jupiter, so it's 3,000 times or more the mass of the Earth, and it's orbiting a star that's not totally dissimilar to the Sun in terms of the size, but it's in this really odd orbit. So this is something that was discovered from the ground about 18 years ago, and so we knew that there was a chance that there might be another planet in that system. So this is one of the first things that we actually jumped onto in terms of analyzing the data. We had a hint that this was a good place to look at. And in fact, Chelsea Wang, who's a Torres Fellow at MIT, was the first author on this paper. So we discovered a super Earth-sized planet. This is a planet that has a radius about twice that of the Earth, and it's orbiting around this fifth magnitude star, and it has a mass of about 4 or 5 times that of the Earth. And this is the transit that we saw from that. This transit is about 250 parts per million, so it's about 10 times deeper than what the system is capable of seeing. But the best that you can do with ground-based systems, because of the atmosphere, is about 2,000 parts per million. So it gives you an idea of how much of an improvement we have by going into space with such a stable system. Yes?
So I do asteroid occultation, and we measure magnitude drop. Can you translate the parts per million into a?
Yes. A millimagnitude is 1,000 parts per million.
So that's what we're talking here.
Yeah. No, this thing is a quote. This is a one part per million is a micromagnitude. So that's 10 to the 4th. If you're doing photometry if you're doing 1% photometry, this is 10,000 times better than that. In terms of the limit, now TESS doesn't go to 1 parts per million. It goes to around 10 or 20, so it's only 1,000 times better. But it gives you an idea. So anyway, then we could then take this curve, this point, and we could figure out where the mass is, and we can determine the radius, and then that allows us to determine the density that the planet actually has. And all this is just from photometry. Well, this part, in order to get this, you're having to do spectroscopy on the system. That takes a bigger telescope. But basically, you're able to then figure out from equations of state what the planet might be made of, in terms of its density as a function of mass. And so that's really that's where the planetary physics really comes into play. So this is another plot. This is another planet that we found, and Diana Dragomir found this. We discovered it with TESS at this location. And the thing that astronomers have been doing for a long, long time is they've been measuring radial velocities from the tugging of the host star for a lot of bright star systems. And this is an 8th magnitude star. And they did, but the data has been marginal. They've not been able to tell was there a planet there or not. And so what we did is we found this object, and then we followed it up, which basically means like we've got a time machine. We go back and look at the observations that we wish we were able to make going forward, but it turns out that this work had actually been done by astronomers on the ground with large telescopes. And you see these this is the radial velocity. See, the actual motion that the lines in the spectra have are really tiny. They're in the range of meters per second. So basically that means that the host star is being tugged back and forth with a motion that's a slow walk. So that's how good these measurements have to be in order to define this. And people have built instruments like this. This is how the first exoplanets were discovered. The so-called hot Jupiters back in the mid-1990s were just this radial velocity method. The transit method then came along later on. So this is the transit pattern that we saw, and then this is that's the radial velocity. And by using these two pieces of information, we end up being able to determine the density of the planet itself. So this is actually a Venus-sized planet, so slightly smaller than the Earth. And this is more information on Diana's paper for this. The thing I should point out is this is another planet in that system. There actually are 3 planets in that system. So we actually discovered a triple planet system. There may be others, and the longer we look for the transits, we'll find more and more of these. And so this is basically that same plot I was showing you before in the pre-TESS era, in terms of there were these few points that were of any quality. And if you're looking for an Earth-like planet, it should lie along this green line. And if it were a very dense planet, with essentially all iron or some very heavy composition, it would lie along this line. Now with TESS alone, we've already started to populate this in terms of understanding what the actual structure of these planets are. Here's Venus, and here's where the Venus and the Earth would be, and then Uranus and Neptune would be up here. So this is the area that we really want to understand. So the data from this is something that's been very exciting to the astronomical community, because we're making the data public within a month or so of how we have to get the data down from the satellite, reduce it, and then deliver it to this place called the Mikulski Archive for Space Telescopes. This is at Space Telescope Science Institute in Baltimore. And so we started doing this early December. And the first 4 days afterwards, there were 3 million downloads and 60 terabytes of data were retrieved. And then lately, the number's just been going up even higher. And right now, TESS is actually distributing 10 times as much data as Kepler and Hubble do. So the data is in a format that it fits images, and people can just go and look at the data and try to look for phenomena that we're not necessarily even finding as part of the team. And then the amateurs are involved in this. The planet hunters, there's 2,500 or so that are being organized by Susanna Graham, who's at Oxford University in the UK, and they're going through and helping us classify these. So far, they've had more than 1 million classifications, because this was just the first week that they started working back in December. So the other thing is that this is all about planets, but it turned out that that's not the only thing that TESS is able to do. With these fields of view that we have, we can also do extragalactic transient astronomy. We can look for things that actually change dramatically in their light output. And that's because the stability of the detectors and the orbit and everything that we're able to do to work with the system allows us with the cameras are only about this big, and yet we can go down to we can do 10% photometry at 18th magnitude, and in fact we can get down to 10 sigma sensitivity at 20th magnitude. So that means when you talk about limiting magnitude, you normally mean something like 5 standard deviations, and that would be magnitude 20.5, and that's what the system just goes to every time we take an image in 30 minutes. And if you think about what this means in terms of things that we know about that are actual transients, and an extragalactic transient is something like a supernova, or Kilinovae, which are the precursors. These are coalescing neutron star binaries. There are supermassive black holes in the cores of active galaxies, and these are things that can cause a sudden brightening of the core of a galaxy. So if you then say, okay, this is a plot that shows the characteristic time scale, where I put these question marks, those are things where you don't see objects or phenomena that people have really studied. It doesn't mean that they're not there, it just means that people have not had the tools observationally to look in those places. And that's the thing that TESS is actually enabling us to do. So for example, in this area out here, we can look for these phenomena all the way out to the Coma cluster. And then for things that have little smaller absolute magnitudes, these are absolute magnitude of 20, 25. So this is where a lot of thermonuclear supernovae lie, and type 1a, which are the ones that are used to demark the expansion of the universe. So there's a region over here where this area through here is not fully explored. After the Virgo cluster, we can look for things that are slightly fainter, and then as you come back in, Andromeda and now the Magellanic Clouds. There's an incredible, it's really quite remarkable, as close as the Magellanic Clouds and Andromeda are. Characteristic transients that have time scales of the order of a day there's very few that are actually known because typically they disappear before astronomers have a chance to actually go back and say, was that a defect in my detector? Did it recur or whatever? So you don't actually get a chance to resolve them. So this is an example of the kind of things that we can see for supernovae. This is again that same plot showing these the 4 cameras. Here's the LMC and the SMC and areas that are closer to the ecliptic. So in this plot, this is the ecliptic pole and that's the ecliptic. So this is the 96-degree strip. And then if I turn this on, that's a supernova that we found. And these are the actual points when it went from below when we could actually detect it to being visible. And the scatter is just because of the way we bend the data. And so we just looked at this, and these were things that just popped out in the initial observations that we made. So when we were done with that, there's 6 of these objects. This was from a relatively short series of data that we looked at. Michael Fastow, who's a postdoc working with me, actually found these. You can do some simple scaling. We've already found 53 of these, so there's a lot more than are shown here. And at the rate at which we're finding, we should find 200 of these in the next 3 years. So it's a really rich set of of new objects that people can do measurements of phenomena that have not really been discovered before. And then something that actually happened this was just reported last week, is we observed the very first tidal disruption event by a supermassive black hole with TESS. And what a tidal disruption event is you've got the supermassive black hole and then a star that's orbiting around it, a normal star, gets a little too close, and then when it actually approaches, it gets into the region in which it gets tidally disrupted and ripped apart by the supermassive black hole, and then you get material that's actually spread out in terms of hot debris around the star. Some of it goes into a closed orbit. It'll be an elliptical orbit, and then it collides with itself, and then there's brightening and dimming, and then some of it is actually thrown out of the host galaxy. So the one that we actually saw is the first one in which we actually saw the turn on of this event. Previously, people have found these things after they've been active for weeks or months, and this one was really bright. It got up to 15th magnitude, and it was producing this enormous amount of energy. The sun, for example, is about 10 to the 32. So this was a trillion times as bright as the sun when it actually went up. So it's 3 to 10 times brighter than the entire Milky Way in terms of its output per second. So it was an incredible thing. Relatively nearby, it was about 115 megaparsecs. And it's the most detailed data set that's ever been obtained for any tidally disrupted event. And we were lucky because it's in the continuous viewing zone. So this, in fact, is the data from that object. When we went to that very first field that we observed, when the system was turned on, it was there all along, undetectable, and then there was that galaxy was. And then on January 21, it turned on, and it was then flagged by a discovery group on the ground when it got significantly brighter. And then this is where it was relative to the ecliptic pole in the south. And then this is the way the turn-on curve actually looks. So this is brand new information that will allow us to really understand the nature of supermassive black holes in active galaxies. And this is that limiting magnitude that I mentioned before. So there's all kinds of observations. This is the TESS curve, and then when we flagged this information to the rest of the community, there were satellite observations, a lot of ground-based spectra, a lot of things that were taken to try to understand that. So anyway, this is I'm coming near the end, but this is the map of the sky that we will have covered in the next. Right now, we're here in 2019, sort of quarter of the way through, a third of the way through. When we finish this area, then we'll go to the north and then do this retiling, and then. In the extended mission, which will be the next three years, we're going to do the the northern ecliptic poles in this area up here. But in addition, we're going to also cover the area along the ecliptic plane. And then when we're done, we'll have covered 94% of the sky and filled in all the gaps. That's the plan. In terms of exoplanets, we'll find a lot more. Blue means the ones that we're expecting to find in the prime mission of 2 years, and then so altogether we'll increase that number by 250% by observing for an extended period. So these are the kinds of things that we'll actually be able to find in this extended mission. And then as far as how TESS sort of fits in with the things that astronomers are planning for new facilities over the next decade. This is our mission right here, 2019, where we are right a third of the way through this. We're right a third of the way through the prime mission, and then the extended mission. These are some other satellites that are going to launch soon. The Webb will launch sometime in 2021. The gravitational wave detectors, LIGO, are operating. We're looking at fields that are going to be potential places where we can find counterparts, gravitational waves, and then finally this large synoptic survey telescope will come into operation in early 2022. So this is the period of time that we're looking at right now, but the mission itself can go on for a long time. This is just 10 years, and if we're lucky and everything keeps working, we can probably do something like this again. And since we're looking at transients, for example, that can pop up at any time, there's value in continuing the mission to do that. But more so even for exoplanets, if we can, every time we measure and remeasure the transits and measure the period more accurately, that means that we can extrapolate that period to future observations that people might want to do with telescopes that we haven't even dreamed of today. And so that's the value of what we're doing. It really is a finder scope for both exoplanets as well as new transits. So that's the story of TESS as it stands right now, and there's lots more to come. So this is what we.
How noisy is the signal from a typical star?
Very, actually. It turns out that the typical stars like the sun, the jitter that you'll get might be easily 50 or 60 parts per million. And so but we do know that there are some stars, typically not G stars like the sun, but their K stars tend to be a little quieter, and some subclasses of F stars are as well. They can be as quiet as 3 to 10 parts per million.
So does the sunspots come from sunspots and things?
Yeah, it's sunspots. It's flaring activity. It's turbulence. Anytime you've seen those pictures of what the sun looks like in H alpha, it's like a boiling cauldron, and that manifests itself as both photometric noise, because those things have different temperatures, but it's also radio velocity noise. So the problem that we would have is we might be able to get a good photometric measurement, but the Doppler measurements are harder to make too. Yes.
In the same vein, photometric, like how many transits do you need to see before you decide to do an exoplanet?
Well, the minimum number is 2, and you like to see 3. But it turns out that there are clever things that you can do even if you've got only a single transit. And then if you can predict when to look again in the future, even based on that basic shape, because you know, for example, there's ingress and egress information, and that will change a little bit depending on how much limb darkening you have in the host star, and there's a lot of information you can tease out even from a single transit. Yes?
What's the projected data life of the detectors? I know that astronauts have to trade out their cameras on board every few years because of cosmic ray. That's another thing.
Well, it turns out that, for example, in the case of Hubble, that's right, because Hubble is in a 28-degree inclined orbit, and it brings it right through the heart of the radiation belts around the Earth. And the doses that you get from the radiation belts around the Earth are 1,000 times worse than what you get when you're outside the magnetosphere, because the flux of particles that we have when we're out in the TESS orbit are just basically galactic cosmic rays, and they don't change very much. Also, the thing that's really wrong with that's disturbing with the protons, which are the worst offenders in the radiation belts around the Earth, is that they're actually, ironically, they're lower in energy. So they produce these huge ionization tracks, and they damage the crystalline structure of the CCDs. Low Earth orbit is not a good place to be unless you're in a very special orbit where you're right along the equator. You don't go through the South Atlantic at all. Yes.
Obviously, you're generating an enormous amount of data, and I'm guessing that you use computers to do some kind of an algorithm or some way to figure out what's happening. Can you talk a little bit about what that looks like?
Yeah, the images that because the CCDs are not damaged to a significant degree, the number of flickering or hot pixels that we get. First of all, the CCDs that we're using were fabricated at Lincoln Lab. They're the best CCDs that anybody has ever flown in terms of their uniformity. The pixel uniformity is of the order of 1/10%, and so they're just really superb devices. They're far better than the ones that you can buy commercially, and then we hand-pick them, and so. That's to say that analyzing the data is a lot simpler because you don't have as many bad columns to worry about. And the other thing is that because we maintain the temperature so uniformly, and the clock levels are all very carefully set, and they stay set because temperature variations in electronics also are not occurring. The data is very easy to analyze. So if I were to anyone who wants to can go to that website and download the FITS images that are associated with it. You can look at them yourselves. The processing that we do actually involves taking the data that's transmitted through the deep space network. It's in a packetized form. We can produce up to 180 gigabytes per 2 weeks. That doesn't sound like much. I mean, in terms of what you have on your laptops, I mean, 2 terabytes is not uncommon nowadays. But the thing is, the satellite is so stable in terms of its performance that we can actually use data compression techniques, either Huffman encoding or LZ encoding. These are different ways of compressing the data, so that the data that initially starts out as being 18 bits per pixel compresses down to about 4, and it's lossless compression in the sense that you have the full information that's consistent with the statistics in the image itself. And so that means that means that equivalently we've got multiple terabytes of storage in terms of if you were to do this the way that
What I was expecting you to say is that your software is looking for dips in in light?
Well, it does, and the thing that you, to answer that question, when you basically put an aperture in software around where a given star is. In fact, the 200,000 stars that we pre-selected, we know exactly where to look. These are the ones that from previous surveys, we know they're relatively close by, and we know the spectral class, so we know approximately what a transit for a given size planet will actually look like. And then what we do is, because there still are variations, you basically take an ensemble of stars in the vicinity, and then you do relative photometry to that. So if something changes in the background levels or anything at the level that would affect the brightness of the star, you basically have hundreds of reference stars that you can use to compare to. And then once you've done that, then you, in the case of those stars, we've got 2-minute data points, and then we can actually look through. And you saw that in some of those papers that you saw the natural scatter. That scatter is primarily in the host star itself, not in the cameras. So there are a lot of details in it, but that's the key idea. It's a really simple way of analyzing the data, except there's a lot of it. Yes?
How do you tease out 4 objects from 1 pixel?
There are 2 things. One is the system is stable, so that if you go to a catalog, like the Gaia catalog, or in some cases other infrared catalogs, you know what the relative positions and brightnesses are for those stars that are in that pixel, and then you can use that information as a prior when you actually go through and do the analysis. The other thing that actually happens, and this is something that was developed for the Kepler program, which is very clever. If you have 2 stars in the image, one of the things that will happen is if you have a transit, one of those stars will actually appear to get fainter, or it'll become slightly fainter when the transit is occurring. And whether it's on the left side or the right side, what you can do is look at how the image shifts, because we defocus the image a little bit. It's 1.5 or 2 pixels wide, and so the centroid will actually move a little bit, and it moves in synchrony with that transit. And so that's another way you can sort all of this out. So that's what those people who were in the team initially, they were exercising these techniques where if we see something that looks like a transit, then you have to be sure that it really is a transit and it isn't some of these false positives that are going to be occurring.
We perhaps do maybe one more question or 2 more questions.
On the back.
You initially, beginning, you mentioned the asteroids. I'm just curious, any planetary scientists have looked at the data to look for asteroids? Is it because like the camera setup? All the asteroids captured by the camera are inspected to be known asteroids.
Well, there are near-Earth objects that we've seen already. The other thing that you get from it that sometimes hasn't been previously studied is that you can look at the light curve. The asteroid is not only moving across, but it's changing its brightness. And so you can see binary asteroids, for example. You can see asteroids that are potato-shaped. I mean, there's all kinds of information that's in the images that you can get. And as I said, there's thousands of these things. The people at the Minor Planet Center are interested. Matt Holman, who's here, is one of the people who are coordinating that. The people at Lincoln Lab are interested, and there's a number of people in the Planetary Protection Office who are doing this.
It's also the Atlas survey underway.
Sorry?
It's also the Atlas survey underway, so there's a lot of asteroid data streaming in at the moment.
There's a lot of asteroid data. The southern hemisphere is something that TESS is providing interesting data to begin with. I mean, it's not the primary purpose, but it's a a byproduct of the survey.
Focal length of the lenses, and are they commercially made?
No, they are not. There's 7 element lenses. There are two of which are A-spheres. The glass was actually obtained from Optimax in Rochester, and we actually made the lenses at MIT at Lincoln Lab. There was a commercial design. One of the neat things about the design is that there's no vignette, so there's no darkening around the edges. If you're used to devices, you notice that. And that's because the L1 is oversized deliberately, so that we work through the ray paths in such a way that it compensates, so that there still is a little bit of a sine theta loss or cosine theta thing. I look at it loss, but that's really small. The residual vignetting is like 1 or 2%. It's a beautiful design.
And is there much of a problem with temperature change when the orbit's close to the Earth versus out by the moon?
No, there isn't. There's no change there. But what did happen, and this is something that we had to compensate for, is that the lenses were fabricated obviously at room temperature, and the operating temperature of the lenses and the detectors is -80. And so we had to, and believe it or not, we made the camera bodies out of aluminum. And so the shrinkage of the aluminum was actually compensated in the system. There's no focus mechanism at all. There's no moving parts, there's no filter. Okay.
Well, I'm sure perhaps Dr. Brick will stick around for a little while to answer any other questions, but let's give him a nice round of applause.